Assalamu alaikum everyone. Welcome to the course of Digital Signal Processing. The book that we are following is Discrete Time Signal Processing by Alan V. Oppenheim. So this is going to be our lecture number 1 and the chapter name is Discrete Time Signals and System. So before starting the actual topic of this course, I'm going to revise what you have learned in Signal and Systems. And by then the class strength will be full so we can continue our new topics. So let's get started with what you have studied already in Signal and Systems. So in today's lecture, I'm going to talk about signals, type of signals, mathematical representation, discrete time signals, which we also call sequences, brief process of obtaining discrete time signals. We will talk about basic sequences and operations. For example, we have unit impulse, unit step, exponential, and the operations are shift, flip, scale, multiply. Then after that we will talk about combining sequences, how we can combine sequences to obtain some other sequence or signal. So how we can obtain sinusoidal using an exponential. So I will give you an example of this as well. And finally we will end our lecture by discussing periodic and aperiodic discrete time signals. And we will also calculate the periodicity of these signals. So let's move on to our first outline, that is signals. So in this slide we will talk about signals. So basically what is signal? That conveys you some information. Now that information will tell you about the state or behavior of the physical system. For example, the speed of the fan, the speed of the car, the intensity of light, all these are signal. I'm talking to you, it tells you about the behavior of my state, like how I'm talking to you. So all these are signals. And why we use signal? We use signal for the purpose of communication. Now this communication can be between human to human and between human to machine. For example, I'm talking to you right now, so I'm conveying you some sort of information. You are saying stop and go to some machine. So for example, if you say start, the machine starts, and if you say stop, the machine stops. So basically what we are doing, we are communicating. Okay, now signals can be represented in many ways. In all the cases, information contained in some pattern of variation. So obviously there are some variation in patterns. I'm not talking with same pattern all the time. The speed of the car is not constant every time. The speed of the fan is not constant. So there is a pattern of variation. Obviously there are going to be some pattern. So like the way I'm speaking, so there is some pattern in it, but there is a pattern of variation in it. So signals are mathematically represented as a function of. Now important thing to note is that a signal is a function of one or more independent variable. So when we say independent variable, what does it mean? It means, for example, I write x of t. So the signal x is a function of this independent variable t. Okay. And when we talk about images, so a signal in case of image is a function of two spatial variables. For example, x, and then we have rows and columns. And what is the brightness here? Let's say 255. So in image you can see that in image we have rows and we have columns. Okay, so for example at this particular point the value is 255. So this is also a signal, but this is a signal of brightness of two spatial variable, whereas this signal is just a function of one independent variable. Anyways, the important thing to note is that a signal is a function of independent variable. So independent is t. We are going to give values to t. Here we are going to give values to rows and columns. Okay. So a common convention and one that usually will be followed in this book is to refer to independent variable of mathematical representation of a signal as time. So here we are not going to talk about special variable like two independent variables, we are just going to talk about time. Okay, so independent variable will be time. So let's move on to next slide. Okay, so I hope that everybody knows that there are many type of signals. At basic level, there is number one, continuous signal. So everything in reality or in nature is continuous. I'm talking to you, it's continuous. There is no break in it. The speed of fan, the speed of car, the temperature, all these quantities are continuous. Okay, so in reality, the signals or the natural signals are continuous. Continuous signal can also be referred to analog. Both analog or continuous are same things. So number one type of signal is continuous or analog. Then we have discrete signals, and finally we have digital signals. So there are basically three types of signals: continuous, discrete, and analog. How we differentiate them? We differentiate them with the help of independent variable. When we talk about continuous signal, in these signals the independent variable is continuous. For example, x of t, so this t is continuous. So this is a signal. So this axis is continuous. So we have continuous values of t. Okay, we have continuous values of t, and we have continuous amplitude. Both x-axis are continuous and both y-axis are continuous. Clear? Now, when we talk about discrete signals, so discrete signal usually do not appear naturally. Okay, so for example, we are doing some sort of senses, we are calculating something, so we use these discrete signal to represent some meaningful information. So in discrete signal, we usually represent discrete signal as x of n. Okay, so n, because of this n, we usually call discrete time signal as sequences as well. So n is a number. N is a number. So in this case, what we are going to have? We have samples 0, 1, 2. So these are discrete values. However, these y-axis will be continuous. Y-axis will be continuous. So you got the basic difference between continuous and discrete. Now, talking about the last signal, there is digital signal. So digital signals are those for which both time and amplitude are discrete. So what we are going to have, this time is going to be discrete. So these are our samples. Let's say 0, 1, 2, and these are amplitudes. Let's say this is 2 and this is 1. So the amplitude are going to be discrete. Okay, these y-axis are going to be discrete. So these are the three basic type of signals. I hope you got it. Let's move on to next slide. Now, as previously I told you that discrete time signal do not appear naturally. Okay, so how do we obtain discrete time signals? One of the most important way of obtaining discrete time signal is sampling. So we sample the continuous signal to obtain discrete time signal, or they may be generated directly by some discrete processes. However, the important way of generating discrete time signal is sampling. So whatever the origin of discrete time signal, they offer many attractive features. The reason we prefer discrete time signals over continuous is that continuous signals have infinite information. You see that the t-axis or the time axis was continuous, so it has values at 0.1, 0.2, 0.3. From 0 to 1 there are infinite values. So your electrical devices cannot process that information. So your digital devices, general purpose processor cannot process that information. So what we do, we discretize the time axis. How do we discretize the time axis? So for example, if this is a signal, what we do, we pick up the, we sample it in time. So I have picked this sample, this sample, this sample, this sample, and this sample. So now this is 0, 1, 2, 3, 4. So these are samples. Okay. Complete signal processing system can be implemented using VLSI techniques. So this is a technique, very large scale integration. So we can use this technique to build a complete signal processing system. Discrete time system can be used to simulate analog system, or more importantly to realize signal informations that cannot be implemented with continuous time hardware. So what we can do, we can use discrete time systems. So in this course we will talk about discrete time system, many discrete time systems. So the point here is to make you understand that discrete time system can be used to simulate, because it is very difficult to make analog systems. Okay, so what we can use, we can simulate analog system using discrete time systems to realize signal transformation, which is very difficult with continuous time hardware. Thus, discrete time representation of signals are often desirable when sophisticated and flexible signal processing is required. So we prefer discrete time system over analog systems because building the hardware of continuous time hardware is difficult. Moreover, the space required by continuous time signal is relatively high compared to discrete time. Let me give you an example of this thing. You might have seen, like, whenever you play a song, it says 16 kilobits per second. When you have a good quality song, it says 128 kilobits per second. What is it? The song that is saved in your computer is sampled. Okay. However, it has sufficient amount of samples to reproduce that song. So everything that is stored in your computer or that is stored in your electrical device or digital system is sampled. Okay. Okay, so in this slide we will talk about the discrete time signals mathematical representation. We also call them sequences. So discrete time signals are represented mathematically as a sequence of number. So this n is basically the sequence of number which start from minus infinity to infinity. So this represents x of n. So this n is the sequence number, and we say x of n, it is means that nth number. A sequence of number in x in which the nth number is a sequence is denoted by x of n. So if we have like x of 0 will represent 0th sample, x of 1 will represent first sample. When we write n, it means nth number in the sequence. So as I've told you, n is the integer. In practical settings, such sequence arise from periodic sampling. As I've told you, we get this type of signal from periodic sampling. And periodic sampling of what signal? Periodic sampling of analog signal. So if you see here, we have an analog signal here. So what we do, this is analog signal x a of t, x analog, t continuous. So what we do, we replace this continuous t with nt, multiple of sampling time. This t is basically the reciprocal of sampling frequency. Okay, so what we do, we replace continuous time with multiple of sampling time. So we get this x of n. Okay, so let me draw it here. Okay, I'm going to draw it on the next slide. I don't have spaces here. So the quantity t is called sampling period. So this is our sampling period and it's the reciprocal of sampling frequency. And now it is not necessary that we always do this type of process to obtain discrete time signal. However, this is the basic relationship to get discrete time signal from analog signal. Okay, so let's move on to next slide. I'm going to draw this for you. So this is the signal x of n. This is the zeroth sample. You can see here, this is the first sample, this is second sample, third sample, fourth, and so on. This is x of minus 1 sample. So how do we do it? So for example, this is our continuous signal. Okay, this is our continuous signal. So what I'm going to do, I'm going to replace this t with nt. Okay, let's say t is equal to 1. T is equal to 1 and n starts from minus 9. So minus 9 into 1. So our first sample will be here. Then n increments and it will go to minus 8. So this is minus 9, this is minus 8, then minus 7, then minus 6, then minus 5. So this is periodic sampling and this goes on. Okay, so you see the gap between these two samples, it's same. That's why we call it periodic sampling. So we are picking up the after regular interval of time. So after a specific period, that is t is equal to 1. Okay, we're picking up the samples. So this is the graphical representation of discrete time signal. Okay, so let's move on to next slide. Now this is an example, shows a segment of speech signal. So this is your speech signal, this one, which is of 32 milliseconds duration. And how this signal is formed, segment of speech signal corresponding to acoustic pressure variation. So this is variation in pressure as a function of time. Okay, so this is Tx is function of time. So what we have done here in B, this is a sequence, this is n, because we have picked up the samples. You can see here, if you zoom it, these are samples. So this sample, this sample, this sample, so these are samples here. Okay, so we have done periodic sampling. So after periodic sampling, how many samples are there? 256. Okay, so 256 samples are there and this is of 32 milliseconds. So how we can verify what is the sampling time? So if you see here, segment of continuous time, sequence of samples obtained, t is equal to what? T is equal to 125 microsecond. So we know that if time is this and samples are 256, so if you multiply these two, 256 microsecond multiplied by 125, sorry, if you multiply 125 microsecond with 256, what you are going to get? You are going to get 32 millisecond. Okay, so let me repeat it for you. This signal is of 32 milliseconds. Then we have sampled it using this time, 125 microsecond. Okay, so if you divide 32 millisecond divided by 125 microsecond, you will get 256 samples. Or alternatively, if you have time and you multiply them with 256 samples, you will get 32 milliseconds. Okay, so there is an example of how you obtain samples from the time. So here we have talked about three things: the total time of the signals, the samples, and the periodic sampling time. Okay, so in this slide we are going to talk about the basic sequences and operations. Okay, so I'm just talking about these operation and sequence just to refresh your memory how we can mathematically define these sequences and operations. So what are the basic operations that we can perform on the sequences? We are calling this sequence because we are talking about discrete signals. So discrete signals and sequence are same thing. We call them sequence because of this n. Because of this n. This is a sequence of numbers as you have seen in previous slide. So relatively easy operations are product sum of two sequences. For example, we are adding these two. So we need to add them sample by sample. Sample by sample means x of 0 will be added with y of 0. If we are going to multiply, we are going to multiply same sample. We cannot do that x of 1 multiply with y of 2. No, we usually don't do that. We need to do sample by sample. Now multiplication of sequence x of n by alpha. It means this is not a sequence. This is just a continuous number. For example, alpha x of n. So it means that this x of n signal is multiplied by alpha. So how it will affect? The amplitude of the signal will change because this is outside n. So amplitude will change. For example, alpha is 2. So 2x of n. This signal amplitude will be multiplied with 2. A sequence y of n is said to be delayed or shifted version of x of n. Now this y of n is said to be delayed or shifted because this is, if I just remove n naught is 0, so x of n or y of n will be same, but here y of n is the shifted version of x of n and n naught is integer. Okay, so you know about like shifting. If n naught is positive, it will shift towards right. Okay, n naught is positive, shift toward right. N naught is negative, shift towards left. So here we are talking about the two basic signals. So we have talked about the operations. The operation for simple multiplication, that is scalar multiplication. So this alpha multiplication is scalar multiplication. Okay, and we'll talk about the operation of shifting as well. So here the unit impulse unit sample sequence is defined as, so we also call this delta function or unit sample. So unit sample is just this thing which is 1 at 0. Okay, so these are n-axis and this is according to this delta function. This is delta of n. Okay, so delta of n is 1 when n is equal to 0, and when n is not 0, it is everywhere it is 0. So this is unit impulse or unit samples, whatever you want to call it, unit sample, because this is just one sample. So this is basic sequence. We are going to talk about this number of times, so just remember its representation. So let's move on to next slide. So another very important signal is unit step. Okay, so we have talked about unit impulse, unit step according to this definition. So these are n-axis. So when n is greater than or equal to 0, what is the value of the function 1? So 0, 1, 2 up to so on. And keep in mind, we are not putting an arrowhead on top of this. This is discrete. This is discrete. Unlike u of t, this is unit step signal in continuous. This was like this. Okay, unit step. However, so this is very important signal, unit step sequence. U of n is 1 when n is greater than or equal to 0, and 0 when n is less than 0. So n is less than 0 here, so it is 0. So these are the few signals. As you can see here, we have unit sample n-axis, then at 0 this is 1, rest of here it is 0, 0. Now unit step, it is 0, at negative side, and at positive side it is 1. This is real exponential and this is decaying real exponential. Okay, now this is sinusoidal. If I just join these, it will look like sinusoidal. So this is sampled sinusoidal, and this is just example of sequence to be represented as sum of scaled. So this is some random signal. Okay, this is some random signal. We can represent this signal with the help of sum of scaled delayed impulses. Okay, so I'm going to talk about how you can represent this P of n using impulses. So we know that there is an impulse at -3, we know that there is an impulse at 1, we know impulse at 2, and we know that impulse is at 7. So anyways, next thing that is important to talk about here, how unit step is related to unit impulse. So we know that how this is related, how we can obtain this, how we can obtain unit step using this unit sample. So you know that if we have many unit samples, if we have this, 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 and we add them, we are going to obtain this unit step. So this is what is happening here. U of n, we can obtain this unit step U of n by adding delta of k. Okay, so if we have delta of 0, we add it with delta of 1, we add it with delta of so on, we can get U of n. However, one thing is missing. We need to shift this. First we need this, then we need to shift it to here, then we need to shift it to here. So we need some sort of shifting. So let's see how this shifting is done in next slide. So this is how we can obtain unit step. This is unit step. Unit step can be obtained if I have delta of n, that is unit impulse. Then I have moved unit impulse to 1 unit right. I'm going to draw it here. So this is unit step 0. Then I'm adding, this is at 1. Okay, then I'm adding, this is at 2. 1, 0, nothing, 0, nothing. So this was original delta of n. This is delta of n minus 1, and this is delta of n minus 2. So if I add this and keep on adding, what I will get, U of n, that is unit step, and we have to sum this. So we know that n is constant, but this number is changing. Here we have n minus 0, n minus 1, n minus 2, then we have n minus 3 and up to so on. So we can replace this changing variable with k. So k starts from 0 and goes towards n. So if I put the values of k here, I will get the same equation here. So this is how I can use delta impulses or unit impulse to generate unit step. Okay. Is this clear? I hope that. So we have used sampled impulse or unit impulse to generate unit step. Now, conversely, what we can do, we can use unit step. We can use unit step to generate unit impulse. So what we have done, this is our unit step. 0, 1, 2, 3. This is U of n. And we are subtracting it from this signal, which is shifted towards right. It means it has nothing on 0, 1, 2, 3. It is shifted towards right. So and this is going on. If I subtract these two, all these will be cancelled. What will be left? Only this. And this is what? Unit impulse. So this is interconversion of how you can obtain delta of n from U of n and U of n from delta of n. So this must be very clear to everybody. So another important sequence is exponential sequence, which is extremely important in representing linear and time invariant discrete signal. So this is our exponential sequence in discrete. A is some scalar, alpha is real number, and A is also a real number, and this n is our sequence number. So we need to know the value of A, alpha, and n. N can be from, we know that n range from minus infinity to infinity. So everything now depends on the value of alpha. For example, if alpha is between 0 and 1 and A is positive, so we can check x of 0, it means that n is 0. A is positive, so we don't need to write A, and alpha is between 0 and 1. For 0 and 1 it means 0.5, let's say. So 0.5 raised to power 0, it will give you anything raised to power 0 will 1. So x of 1 we will move to forward 0.5 raised to power 1. So 0.5 raised to power 1 is 0.5. So we can see that if I select this value of alpha, we are going down. It means that decrease with n increasing. We are increasing n. You can see that first we have value of n0, we have value of n1. So if alpha is between 0 and 1, we will have a decaying sequence. If alpha is between minus 1 and 0, what will happen? The sequence will decrease. We can check that x of 0 is equal to, and A is positive, so just forget about A. So minus 1 or 5, so we can have value minus 0.5. Minus 0.5 raised to power 0 is equal to 1. Then we have x of 1, let's say, minus 0.5 raised to power 1 is equal to minus 0.5. So this is again decaying, but with alternate sign. Okay, so here we have decreasing sequence for this alpha. Here we have a decreasing sequence with alternating sign. So 1 minus 0.5, again next will be 0.25. And lastly, if we have alpha greater than 1, so you can put alpha greater than 1, that is 1.2 or 2, 3, 4, 5, whatever you want to put. The sequences grow in magnitude. The sequence will grow in magnitude. It means with as you increase n, the sequence will increase. So I hope that there are few pictures that I can show you in next slide. So let's move on to next slide. Okay, so we do not have any picture, but I'm just going to draw that for alpha between 1 and 0, we will have a sequence like this. This will be starting from, let's say, 0, and it is decaying. Okay, this is for first. Then we have alternating sign. So 1, decrease, 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 decrease. It is decreasing but with alternating sign. And finally, for alpha greater than 1, we have growing sequence. So 0, 1, 2, 3, 4. As the values of n increases, the sequence grows. It will grow. This was decaying. Okay. So in this slide, we will talk about combining sequences. So we will use an exponential sequence. So this is an exponential sequence. We have already talked about this. What we have done now, previously x of n was equal to this. There was no restriction on n. We can choose n between minus infinity and infinity. But here we have restriction on n, that n must be greater than or equal to 0. So we know that I can combine a alpha n with u of n, because u of n is on the positive side only. Okay, so if I write this or I write this, these are both same. X of n is equal to a raised to power n, a raised to power x of n is equal to a alpha power n. If I write this n greater than equal to 0, or I write u of n, both are same. So what we are doing, we are multiplying this sequence with u of n, so it will be only on the positive side. I hope you have studied all this in previous course. So we can obtain sinusoidal signal from this basic expression. So this is our exponential sinusoidal sequence. So x of n is equal to a cos of theta. So this whole is our theta. So theta is omega naught n plus some phase phi, and we can have any value of n here for all n, that is from minus infinity to infinity. A and phi are real constants. So this is real constant, this is real constant. This omega naught is the angular frequency and this n is the sequence number. And this angular frequency is radian per sample. Okay, radian per sample. So let's move on to next slide. So here you can see that what we are going to do, we are going to consider a alpha n with complex alpha. So alpha is complex now. We know that when alpha is complex, it will have magnitude and it will have phase. Okay, so that alpha is in polar form. It has some magnitude and it has some phase. It is e raised to power j omega naught. Likewise, a is also complex. So if a is complex, a will have a magnitude and a will have a phase. So what we are going to do, we are going to substitute the values of a and alpha here. So a is equal to this thing, so we have this, and alpha is equal to this. So because alpha has power n, so we will have alpha power n e raised to power j omega naught n. Now, and just for simplification, we know that the bases are same. So we have j here, we have j here, so we can take j common, e raised to power j omega naught n. And this is just the magnitude. Okay, so everybody knows that e raised to power j theta, this is Euler identity, is equal to cos of theta plus j sine theta. So this is what is done here. So this is just magnitude, so cos of this theta, this is our theta, plus j sine of theta. So this is multiplied with both of these two. Okay, so this was like this. If you open this, so we will multiply this magnitude with both the quantities. Okay, so j a magnitude alpha and sine of theta. So now we know that this is sinusoidal, this is sinusoidal. Okay, we know that this is sinusoidal, but we know that a magnitude alpha raised to power n. Now the sequence oscillate with exponentially growing envelope. We know that if alpha magnitude is 1, if the value of alpha is greater than 1, the sinusoidal will grow, it will grow. Okay, if alpha is less than 1, it will decay. If alpha is less than 1, it will decay. So the exponential envelope will decay or increase. If alpha is equal to 1, if this is 1, so this will be referred to as complex exponential sequence. So if this is 1, it will just be a sinusoidal sequence. Okay, so x of n is equal to, we have alpha 1 here, so a magnitude e raised to power j omega naught n, this is equal to a magnitude cos of omega naught n plus, so this is just our complex exponential with no increasing and decreasing. Okay, so here we have considered the case of omega naught is equal to pi. So we know that if we put omega naught is equal to pi, so cos of 180, so we know that cos of 180 is 1, so this is going to be 0. Okay, So this is going to be 0 because sine of 180 is 0. So if we put any value of n, that is 0, 1, 2, 3, it is going to be 0. So we will only left with this real quantity. We will not have any complex here. Okay, but when we consider alpha mod is equal to 1, this sequence is referred to as complex exponential and has the form this. Let's move on to next slide and just simplify it further. So so the fact that n is always an integer, this n, we know that this is always an integer. In equation 2.15, there is our previous equation, lead to some important differences between properties of discrete time and continuous time. So there is a huge difference between continuous time signal and discrete time signals. An important difference between continuous time and discrete time is seen when we consider frequency. Now, omega naught plus 2 pi, if you add 2 pi to any discrete angular frequency, this is undistinguishable. It means that it will not make any difference. So this is our exponential sequence a e raised power j omega naught. We have just added this thing ourselves. So if you add this, this will again become e raised power j omega naught. And why? Because you see that here e raised power j to this is equal to 1. Why this is equal to 1? E raised power j 2 pi n. Let's take a value of n to be 0. If I take n to be 0, this will become e raised power 0 and this is equal to 1. Even if you take n is equal to 1, it will become e raised power j 2 pi. And if you expand this, this is equal to cos of 2 pi plus j sine of 2 pi. We know that cos of 360 is equal to 1 and sine of 360 is equal to 0. So this will again become 1. Okay. So this is important that in discrete, when we add 2 pi to omega naught, that is our angular frequency, this will become undistinguishable. So after 2 pi, we cannot differentiate between the signals. More generally, we can easily see that complex exponential equals the frequency omega naught plus 2 pi. Now it can be 2 pi, it can be like 4 pi, it can be 6 pi, where r is integer, is indistinguishable from another. An identical statement holds for sinusoidal sequence. So because sinusoidal and exponential are same, so we can write a cos omega naught plus 2 pi r n plus phi. So previously we were not using this term, okay, so we're using cos omega naught n, but if we add this term, that is 2 pi r. So this and this both are equal. Okay, so we must need to consider that if we add 2 pi or 2 pi r, where r is integer, these signals are indistinguishable. We cannot differentiate between them. So we're going to talk about these indistinguishable signals in chapter number 4. For now, we simply conclude that when discussing complex exponential signals, for example, this is our complex exponential signal, or a real sinusoidal signal which is of this form, we only consider frequencies in the range. So we know that a signal is indistinguishable after 2 pi. So we consider the frequencies between minus pi to pi or between 0 to 2 pi. We do not take like 3 pi, 6 pi, 4 pi. No, we only take the frequencies between minus pi to pi or 0 to 2 pi, because after that signal is indistinguishable. Another important difference between continuous time and discrete time, exponential and sinusoidal, is their periodicity. In continuous time case, sinusoidal signals or complex exponential signals are both periodic. Continuous, what happens in continuous? That sinusoidal and complex exponential are both periodic. We always say that this is a sinusoidal signal, this is periodic, with the period equal to 2 pi divided by the frequency. In discrete, a periodic sequence. Now in discrete, a periodic sequence must need to hold this condition, that x of n is equal to x of n plus, this is period. Okay, this is period. So it means that x of n, if for example if I say that the period of a signal is 2, so 0 plus 2, so this sample value on x of 0 should be equal to x of 2. Okay, this statement must hold. Likewise, for this is for normal sequence and this is for sinusoidal. So for sinusoidal sequence, this is our sinusoidal sequence. So what we are going to do here, you see we are adding in n. So a cos of omega naught n. Now this is frequency plus n. Or we can simply do it like this, omega naught n plus n. Both are same thing. And omega naught, we know that omega naught is equal to, which is everybody knows that omega naught is equal to 2 pi k divided by n. Okay, or n omega naught is equal to 2 pi k. So we require that omega naught n is equal to 2 pi k. As I have already told you that at this point we need to add 2 pi. If we add 2 pi r, this and this are equal. So that's why we have said that omega, this quantity omega naught n is equal to 2 pi k. K is an integer, and a similar condition hold for complex exponential. So here are the few examples of periodic and aperiodic sequence which you need to look at yourself. So I'm just going to go through it really fast. Consider a signal x1 of n, which is equal to cos pi n by 4. So here omega is equal to pi by 4. Okay, this is our omega. Now the time period is also given to us, that is n is equal to 8. So n is equal to 8. Okay, this is given to us. To show this, note that x n plus 8. Now if I add n plus 8, it means that I am adding cos pi by 4 n plus 8. Okay, so this will become cos of pi n by 4 plus 2 pi. So we know that if there is addition of 2 pi, 4 pi, this is equal to cos of pi n by 4. So this and this are equal. So these two are equal. These two are equal. So it means that n is equal to 8 is the period of this signal. Now, satisfying the definition of discrete time, now consider another example. So it is not necessary that if we increase the frequency, the period will decrease. Normally what happens, if we increase the frequency, it means that repetition are actually happening faster. So n should go, the period should go down. But this is not true in the case of discrete signals. Keep in mind that if I'm increasing the frequency of a fan, the fan will rotate faster and the period will come less. But this is not true in the case of discrete time. Increasing the frequency might increase the period, or it will make the signal aperiodic. So let's have a look at the second example. Here, if you see here, the frequency is 3 pi by 8, which is obviously greater than pi by 4. So frequency is what? 3 pi by 8, which is greater than pi by 4, which is higher frequency than x1. However, x2 of n is not periodic with period. You see, we have increased the frequency, but this is not periodic with period 8. Why? So similarly, we are adding 8 to x2 of n. So 3 pi by n plus 8 divided by 8. So this will become cos 3 pi by 8. So this is same thing. But here we have 3 pi. What we required here was 2 pi. 4 pi multiple of 2 pi. So this is not periodic. So this, because if you solve this, this will become minus x2 of n. However, we require x of n. Using an argument analog this to the 1 x of n, we can show that x of 2n has a period 16. So if I write 16 here, it means that if I use period of this to be 16, then I can solve it for you. So let's find out the period first. Find out the period of this x2 of n. Find out the period. How we can find out the period? We know that omega n is equal to 2 pi k. Okay, so omega here is 3 pi by 8, n is equal to 2 pi k. Pi cancels with pi, and then we have 3, n is equal to 16 k. Now n is equal to 16 divided by 3 k. Keep in mind, in discrete the time period will always be discrete. We cannot have time period 1.2, 1.3, 5.6, 5.7. The time period must need to be discrete. So what discrete value of k we can take so that n become discrete? The only value that we can take of k is 3. So if I take k is equal to 3, 3 cancel with 3, so the time period is 16. So it means to say that if we have time period 16, only then this x2 of n will become periodic, thus increasing the frequency from 2 pi by 8, 2 pi by 8 means pi by 4, to omega naught is equal to 3 pi by 8, also increase the period. This occurs because discrete time signal defined for only integer indices. Likewise, cos 3 n, there is another signal cos 3, sorry, x3n is equal to cos of n. Now we see that there is no frequency. We can only put n is equal to 0, 1, 2, 3, 4, 5. So this signal will not be periodic at all. The integer restriction on x causes some sinusoidal not to be periodic. For example, there is no integer value such that x3 of n is equal to cos of n satisfy this. This signal does not satisfy this condition, so this is not a periodic signal. So let's finally look at few graphs. So as I've told you, the frequency varies from minus pi to pi, or we can say 0 to 2 pi. So here the frequency is 0, there is no oscillation. Here the frequencies increase a bit, that is pi by 8, or we can say 15 pi by 8, both are same. So here there are oscillations. Okay, here the frequency is increased more. This was pi by 8, this is pi by 4. The frequency is increased more oscillations. Here the frequency is maximum. So in discrete time the maximum frequency is pi. Okay, 0 to pi the signal will start oscillating faster, and pi to 2 pi it will decrease. So you can read this cos omega naught for several different values. Omega naught increases from 0 to pi, the sequence oscillates more rapidly. As omega naught increases from pi to 2 pi, the oscillation become lower. So if you see here pi, we are going towards pi by 7 pi by 4, 15 pi by 8, and then 2 pi. Oscillation reduces. So 0 to 2 pi oscillation increases, pi to 2 pi oscillation decreases. So that was about it. Thank you very much.